got those eyes staring into my soul. You get that smile when I'm giving you my all. You're the brighter side of things, you're the lighter side of life, and all the
The KK-2 is a flight control board for multi-rotor aircraft that stabilizes the copter during flight. Built into the controller is a 3-axis gyro accelerometer that determines the quadcopter's roll, pitch, and yaw orientation. The signal is processed and passed on to the electronic speed controllers, which make fine adjustments to the motor's rotational speed, stabilizing the quadcopter, in this case maintaining level flight. Flight controller also uses signals from the radio system's aileron, elevator, throttle, and rudder inputs. This information is processed by the board, and signals are also sent to the speed controllers to control flight. This flight control board is what is known as a PI controller. This type of controller is a control loop feedback mechanism that provides the dynamic system with control by continuously applying a correction to maintain a desired state. With a quadcopter, our desired state or set point is a level attitude.
Looking at a block diagram of the system, we can follow along and see how the controller is able to self-level the quadcopter and maintain this attitude. The gyro accelerometer signal is sent from the flight controller back into the system, and an error E is determined from how far off the current position is from the set point. This error term then gets passed into the proportional and integral terms, which apply a correction. This signal is then sent to the controller, then the new attitude position is returned through the control loop until ultimately the quadcopter will reach the desired set point or level flight.
The proportional and integral factors are what give the PI controller its name. The proportional term is how far the current attitude is off from the set point, proportional to the error. This integral term accounts for the past values of error and then integrates them over time. This term eliminates the steady-state error that occurs with a pure proportional controller. How both of these terms affect the performance is based on their respective gain values. The next clips demonstrate the effect of different P and I gain values on the performance of a quadcopter about the roll axis. To perturb the system, a quick control input causing a roll moment is performed.
First, the P and I gains are set to 0. As could be expected, this setting effectively eliminates the control loop. When doing this, the quadcopter rolled and control will be straight into the ground without returning to level flight.
Next, the P gain is increased to a high value and the I gain is left at 0. In this state, it is only under proportional control and some oscillations can be seen.
Here, the P gain is kept at a high level and the I gain is also set high. The I gain is too high, so there is a lot of oscillation.
Finally, the P and I gains are set to values that are well tuned for this quadcopter. Here, the quadcopter is responsive to the perturbation and quickly snaps back to level flight with minimal overshoot or oscillation. As you can see, quadcopters rely heavily on the use of a control algorithm. Without a PI controller, this quadcopter would be near impossible to control and would likely end up in the dirt. Here's a quick slide overviewing the specifics of this dynamic system. Thanks for watching.